Warm, moist air meets cool, dry air. Tornado formation begins when two very different air masses collide. Typically, warm, moist air from the Gulf of Mexico moves northward and meets cool, dry air from the Rocky Mountains or Canada. This contrast in temperature and humidity creates atmospheric instability, a key ingredient for severe thunderstorms. The warm air wants to rise because it's lighter, while the cool air wants to sink. When these air masses meet, the warm air is forced upward, fueling powerful updrafts that form the foundation for thunderstorms. The role of the thunderstorm. Not every thunderstorm spawns a tornado, but nearly all tornadoes form from severe thunderstorms, especially supercells. These massive storms have a persistent, rotating updraft called a mesocyclone. For a tornado to develop, the thunderstorm must be strong enough to sustain upward motion for a long period. Supercells provide a consistent source of rising warm, moist air and have the right internal structure to support the rotation that eventually extends down to the ground as a tornado. Wind shear. Changing wind with height. A crucial factor in tornado formation is wind shear, which means the wind's speed and direction change with height. For example, near the ground, the wind might be from the south at 10 miles per hour, but higher up, it could be from the west at 50 miles per hour. This difference creates a horizontal tube of rotating air in the atmosphere. By itself, this tube lies flat and doesn't cause a tornado, but it's an essential precursor for the vertical spin that tornadoes need. Tilting the rotation vertically. The powerful updrafts in a thunderstorm can tilt that horizontal rotating tube upward. As the warm, moist air rapidly rises, it pulls the spinning air into a vertical orientation. Once the rotation is vertical, it can begin to intensify and tighten, much like an ice skater spins faster when pulling in their arms. This tilting is a key moment in the birth of a tornado because it transforms the invisible rotation into something that can reach from the cloud base to the ground. Formation of the mesocyclone. Once the horizontal spin is tilted, it develops into a mesocyclone, which is a rotating column of air several miles wide within the supercell thunderstorm. The mesocyclone is not yet a tornado, but it's a necessary stepping stone. It represents the organized rotation that can later extend downward. Doppler radar often detects mesocyclones as areas of strong rotational winds, giving meteorologists an early sign that a tornado might form. The downdraft's role. While updrafts are crucial for feeding the storm, downdrafts, especially the rear flank downdraft, RFD, play an equally important role in tornado formation. Downdrafts are currents of cool, sinking air on the backside of the storm. As the RFD wraps around the mesocyclone, it can help concentrate the rotation near the ground by tightening the circulation and lowering the pressure. This process can create the funnel that we recognize as a tornado. Lowering of the cloud base and wall cloud formation. As the mesocyclone strengthens and the RFD wraps around it, the cloud base near the center often begins to lower into a feature called the wall cloud. A wall cloud is a visible sign that the storm's rotation is intensifying and descending closer to the ground. Tornadoes often form beneath these wall clouds. Observing a rotating wall cloud is one of the most reliable visual cues that a tornado is imminent. Funnel cloud development. When the rotation becomes concentrated and strong enough, the pressure inside the column drops, causing the humid air to condense into a visible funnel cloud. At this point, the funnel may not yet be touching the ground, so it's not officially a tornado. However, the funnel's appearance is a critical sign that the storm's rotation is intensifying. Often, debris or dust at the ground beneath the funnel is the first indicator that the funnel has made contact and a tornado has formed. The tornado touches down. A tornado is officially born when the rotating column of air connects the cloud base to the ground. At touchdown, the tornado can rapidly intensify, with wind speeds ranging from 65 miles per hour in weak EF0 tornadoes to over 200 miles per hour in EF5 tornadoes. The vortex becomes a destructive force, capable of uprooting trees, demolishing buildings, and hurling debris over great distances. Many tornadoes remain on the ground for only a few minutes, but some can last for over an hour and travel dozens of miles. The inflow of warm, moist air to sustain itself. A tornado relies on a continuous inflow of warm, moist air. This inflow feeds the updraft within the supercell and maintains the low-pressure core of the tornado. If the supply of warm air is cut off by rain-cooled air or shifting winds, the tornado can weaken and eventually dissipate. The balance between the inflow and the downdrafts determines how long a tornado lasts. Rain-wrapped tornadoes. Sometimes heavy rain from the thunderstorm wraps around the tornado, hiding it from view. These rain-wrapped tornadoes are particularly dangerous because they're nearly invisible to the naked eye. People may not realize a tornado is approaching until it's too late. Meteorologists rely heavily on radar to detect these hidden tornadoes since visual spotting is difficult or impossible. Multiple vortex tornadoes. In some cases, a single tornado may consist of multiple smaller vortices rotating around a common center. These subvortices can cause localized areas of extreme damage, often leveling one building while leaving a neighboring one standing. Multiple vortex tornadoes are usually associated with stronger tornadoes, EF3 and above, and contribute to the complex and uneven damage paths observed after major tornado events. Tornado dissipation. Tornadoes rarely last long. Most dissipate within minutes to an hour as the storm's structure changes. As the supercell's updraft weakens or becomes disrupted by cool downdrafts, the rotation near the ground loses its supply of warm, moist air. The funnel becomes thinner and more rope-like before finally disappearing. This final stage, often called the rope-out phase, can still be dangerous, but the tornado is usually much weaker. The role of geography. Geography plays a significant role in tornado formation. The central United States, often called Tornado Alley, is particularly prone to tornadoes because of its unique topography. There are no major east-west mountain ranges to block the collision of warm, moist air from the Gulf and cold, dry air from the north and west. This setup creates ideal conditions for the formation of supercells and, ultimately, tornadoes. The importance of radar and forecasting. Modern meteorology uses Doppler radar, satellite imagery, and computer models to track storms and identify signs of tornado development, such as mesocyclones and velocity couplets. These tools allow meteorologists to issue timely tornado warnings, often giving people minutes to seek shelter. Research missions like Vortex and TWISTEX have also deployed instruments in the paths of tornadoes to collect valuable data, improving our understanding of how these storms form and behave. Tornado myths and misconceptions. Many people still believe myths about tornadoes, for example, that opening windows will equalize pressure and save a house, or that tornadoes can't cross rivers or mountains. In reality, none of these are true. Opening windows can actually increase damage by letting high winds enter the building, and tornadoes can cross rivers, climb hills, and strike urban areas. Understanding the science of tornado formation helps debunk these myths and encourages people to take proper safety precautions. Climate and seasonal patterns. While tornadoes can occur at any time of year, they are most common in the spring and early summer in the northern hemisphere. This is when warm, moist air from the south is most likely to collide with cooler air from the north, creating the unstable conditions needed for supercells. Climate patterns such as La Nina can also influence tornado activity by affecting the position of the jet stream and the distribution of warm and cool air masses. Ongoing research. Despite decades of study, scientists still don't fully understand why some supercells produce tornadoes while others don't. Ongoing research focuses on the small-scale processes inside thunderstorms, including the interaction of updrafts and downdrafts, the role of humidity, and the behavior of wind shear. Advances in radar technology, drones, and computer simulations are helping scientists get closer to solving these mysteries and improving tornado forecasting.